2-minute anaesthesia pulse oximeter. The pulse oximeter is a probe which determines the amount of oxygenated hemoglobin and expresses it as a percentage and a waveform. It's composed of two LEDs, one which emits red light at 660 nanometers and the other one infrared light at 940 nanometers. You insert your finger. Your finger has an arterial pulsation which accounts for 2% of the signal, and on the opposite side of the finger there's a photodetector. As the width of the finger is relatively fixed, the only factor which changes is the arterial pulsation, which, as mentioned, accounts for 2% of the signal. We are able to extract the oxy and deoxyhemoglobin from this part and analyse it to give a percentage. The greater the absorption by the heme molecule, whether it's oxyhemoglobin or deoxyhemoglobin, the less detected by the photodetector. We can therefore compare these two values to give an oxygen saturation. There's two important graphs to look at. The first one compares oxy and deoxyhemoglobin at different wavelengths and the absorption. The maximum absorption is at deoxyhemoglobin is 660 nanometers and oxyhemoglobin is 940 nanometers. Where these two lines cross, this is known as the isobestic point, and this occurs at 805 nanometers. This allows quantification of the concentration of hemoglobin. The next graph looks at Bayes' law, or Beer-Lambert law, or Lambert-Beer law. It's a linear relationship between the concentration and the absorption. So as the concentration increases, the absorption increases in a linear fashion. Pulse oximeters or saturation probes have two LEDs which flash at a set determined sequence at two wavelengths. Based on the Beer-Lambert law, as the amount of a substance increases, the absorption also increases, therefore the amount detected by the photodetector is less. The microprocessor is able to compare the absorption between these two wavelengths to determine the saturation. As the absorption increases, therefore the amount detected is less. So in order to get the characteristic appearance of the arterial pulsation, the signal is flipped from a negative signal to a positive signal. There's a range of controllers and filters which also help to detect and improve the signal. The gain controller controls the intensity of the light emitted to compensate for changes in finger thickness and skin colour. Bypass filter extracts the AC component, i.e. the pulsatile component. Abnormal readings can be due to artifacts from diathermy, motion, low perfusion, or they could be due to falsely high from carbon monoxide or cyanide, or falsely low from dyes and methemoglobinemia.